This lesson is focusing on past paper questions for sequences and series, so APs, GPs, and binomials. But these are the questions that are a little bit different. So not your standard, let's just learn the things and apply the formulas kind of questions. Questions where we need to think a little bit more and have a little bit more fun. So starting off with our first one, we have three geometric progressions, P, Q, and R. And they are such that their sums to infinity are the first three terms, respectively, of an arithmetic progression. We have progression P, which is 2, 1, half, quarter. We have progression Q, which is 3, 1, third, and ninth. So they ask us to find the sum to infinity of progression R. So in order to do the sum to infinity of progression R, we're going to need A over 1 minus R. So we're going to need the A and we're going to need the R. How are we going to get these? Well, they told us the sums to infinity are the first three terms of an AP. So we have an AP, which is sum to infinity of P, sum to infinity of Q, sum to infinity of R. So if we can get P and Q, we can get that sum to infinity of R because this is just an AP, so we wouldn't actually need to go our traditional route. So you see how important it is to get that information out of the question. So we need to then get sum to infinities for P and Q. So for P, we know that A equals 2. So I'm just using a subscript of P to keep myself in line in terms of which sequence I'm working with. R of P is 1 divided by 2, so it's a half. So the sum to infinity, so for P, sum to infinity equals 2 over 1 minus a half, which equals very simply 4. So we've now got this first term here. We know this is going to be a 4. So now we do the same thing for Q. For Q, we have A of Q equals 3. R of Q equals 1 over 3. So for Q, sum to infinity equals 3 over 1 minus a third, which is going to give us 9 over 2. This means now that we've got the first two terms of our AP. So therefore, our AP equals 4, 9 over 2, sum to infinity of R. So we need a D. And if we just add on a D, we'll have the sum to infinity of R. We know that A equals 4. We know D equals 9 over 2 minus 4, which equals half. So therefore, the sum to infinity of R equals 9 over 2 plus 1 over 2, which equals 5. So a very different way to find the sum to infinity. We didn't actually use that sum to infinity formula to calculate for R. We used the idea of this relationship that the sum to infinities form an AP. So as much as we learn these sort of traditional questions, it's always important to bear in mind the sort of full breadth of what you're doing, so that when you get something slightly more funky, then you can go ahead and solve that too. Moving on to the second part of this question. Given that the first term of R is 4, find the sum of the first three terms of R. Okay, so this will be the A. Sum of the first three terms is S3. So to get S3, we need a times 1 minus r cubed over 1 minus r. So we've got an a, that's fine, we're given that. We need to calculate the r. But we've got the sum to infinity, so we can work backwards to the r. So, for value of r, we know that 5, the sum to infinity, equals a 4 over 1 minus r. So 1 minus r equals 4 over 5, and r equals 1/5. So now we've got the a, we've got the r, we can go ahead and plug in to calculate that sum of the first three terms. So, for sum, S3 equals, a is 4. 1 minus, we're using the fraction, then we put it in the brackets. Cubed over 1 minus 1/5. So this gives us 124 over 25. And we check back at our original question. The original question worked with fractions. So we wouldn't actually want to give a decimal answer here. But 124 over 25, that's rather a majorly top-heavy fraction. So let's take it down into a mixed number. This is 4 and 24 25ths. So our sum of the first three terms for r is 4 and 24 over 25. So from a GP to an AP, we've got to treat them both equally. The first two terms of an arithmetic progression are 16 and 24. Find the least number of terms of the progression which must be taken for their sum to exceed 20,000. So not your usual type of question, but you can apply that same process of summarizing and building equations. So we have an AP. First two terms. So A equals 16, U2 equals 24, equals A plus D, so 16 plus D. We can see straight from here, therefore D equals 8. Find the least number of terms for the progression which must be taken for the sum to exceed 20,000. So we need the sum of n to be bigger than 20,000. So we can then never leave things as an Sn. So it would be 1/2 n. 2a, well in this case a is 16. 2a plus n minus 1, nothing we can do with it, times d is greater than 20,000. And you see here now, we've gone straight to just one variable, and it's an n. So it's not a traditional question, but it behaves and responds to exactly the same method. So we can then say that n, this is 32 plus 8n minus 8, and this is bigger than 40,000, just clearing that fraction to get it out the way. So then if we open up, 32 minus 8 gives us 24 times n, so 24n, and then n times 8n would give us plus 8n squared, still bigger than 40,000. So we've obviously got a quadratic forming here, and there's an inequality, so keeping our eyes on everything. 8n squared plus 24n minus 40,000 greater than 0. Why work with the coefficient so enormous if we can take it out? All of these are divisible by 8. N squared plus 3n minus 5,000 greater than 0. Quadratic inequality. There's no way around it. You're going to have to actually deal with that quadratic inequality as part of your working. So we then have to go for critical values. N squared plus 3n minus 5,000 equals 0. Factors of 5,000 which subtract to 3, I'm not even going to go there. So n equals minus b plus minus square root. B squared is 9 minus 4ac, 4 times 5,000 plus 20,000. Not missing any zeros. All over 2a. So we get n equals, with the use of a calculator, not the use of our heads, I have to admit. Don't know what the square root of 20,009 is. 69.2, and n equals minus 72.2. Right. So, now though, this is not what we would traditionally do with this. We've always got to be working with this application. Okay, so we would then be looking at this as a quadratic. Minus 72.2 and 69.2. But remember, n is a number of terms. We can't have minus 72.2 terms. So this whole side is not applicable. So we want, the quadratic is greater than 0. So we want this piece here. But we also can't have bigger than 69.2. We can't have 69.2 terms. We've got to think that a little bit further and say, well, if we need 69.2, we obviously 69 is not big enough. So the smallest n that we could have in this case would be 70. So therefore, smallest number of terms equals 70. We need 70 terms in order for our sum of the terms to exceed 20,000. If we only have 69 terms, we're not going to make it over 20,000. We need 70 terms. So, still, straightforward working through a summary, but then also thinking a little bit further once we get to our quadratic inequality. Yes, we've still got to do critical values, we've got to understand what's going on here, but we've got to take it a little bit further in our interpretation. Not just giving an answer to a quadratic inequality, but using this method as something that we are using to answer our question, rather than just answering a simple quadratic inequality. Are you happy with this change of use of the quadratic inequality? Okay, cool. So let us move on to part B of this question. A geometric progression has a first term of 6 and a sum to infinity of 18. A new geometric progression is formed by squaring each of the terms of the original progression. Find the sum to infinity of the new progression. So again, closely related, just a little bit twisted. So we know that the first geometric progression, so GP1, we know that A equals 6, and we know the sum to infinity equals 18. Okay, and we know that we don't leave it as a sum to infinity, it becomes 6 over 1 minus r. We know that our second GP, what do we know about it? It's formed by squaring each of the terms of the original progression. So if A is 6 for the first one, A is 36, 6 squared for the second one. So we've now got to get the sum to infinity of the new progression. We've got the A, but we don't have the R. But if we can get the second term of the first GP, we can get the second term of the second GP, and we can start working to build our body of knowledge. So this one, it's about tracking where you are and where you're going to make sure that you're on the right track. So we're going to start out by finding R of that first GP. So for R of GP1, we know that 18 equals 6 over 1 minus R. So 1 minus R equals 6 over 18, which is a third. So R equals 2/3. Then if we have the second term of the first GP and the second term of the second GP, we can get the R of the second GP. So for second term of each. So for our first GP, GP1, U2 equals 6 times 2/3. So 6 times 2/3 gives us 4. GP2, remember we're just going to square each term. So U2 would be 4 squared would be 16. So now we've got the first term and the second term of the second GP, so we can get the R of the second GP. So for R of GP2, R equals, in this case it will be 2 over 1, so 16 over 36, which gives us 4 over 9. So now we've got for our second GP our A and we've got our R, so we can calculate that sum to infinity of the new progression. So sum to infinity of new progression equals 36A over 1 minus 4 over 9, which equals a very complicated number, 64.8. So our final answer, as a decimal in this case, there's no big fraction work in any part of this question, and 64.8 is lovely and neat. So we leave it as it is. So again, using these subheadings to break up your answer and help track what have you got, where are you going, what do I need, where am I working, all of these sorts of elements of your answer is really helpful. It's helpful to you when you go back and check it. It's helpful to your examiner when they mark it. So it's really worthwhile building that habit of breaking your answer down into pieces. We've done APs, we've done GPs. So of course, next comes binomials. So the first one is actually a very normal question. Find the first 3 terms in ascending powers of x in the expansion of 1 plus x to the 5. So 1 plus x to the 5 equals, and we just go for it because we know it's going to turn out in ascending powers if we do it correctly. So the first one will just be 1 to the 5 plus 5, 1 to the 4 times x plus 5, 2, 1 to the 3 by x squared plus dot, 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 but we're not going to carry on because they just want that first 3 terms. So this equals 1 plus 5x plus 10x squared. Done. And then we look at the second part. The coefficient of x squared in the expansion of 1 plus px plus x squared all to the 5 is 95. Use the answer to part 1 to find the value of the positive constant p. So we're going to get 2 answers for p and we're going to conclude that only one is applicable. So we have to look at this messy thing here and say, how does this relate to my original question? And if we look at it closely, we see a 1 plus something to the 5. And here's a 1 plus something to the 5. So if we pull this out here, this px plus x squared, that in effect is our x from part 1. So now we have to think about, if instead of having x and x, we had px plus x squared in each of these things, how would we make an x squared term? Because we've got to build this expression for the x squared term in order to get the coefficient to equate for 95 and to solve for p. So let's have a look at it. We know that 1 plus x all to the 5 equals 1 plus 5x plus 10x squared. Plus, we don't need the bigger ones because they would be exponents that we wouldn't be working. So what we then have actually is 1 plus px plus x squared to the power 5 is 1 plus 5 times what was in that x position, px plus x squared, plus 10 in the x position, px plus x squared. But this would be squared because our x here is squared. So now we have that substituted form so that we've got a better idea of what we're looking at. And we say to this, and we say, okay, how out of all of this would we build an x squared term? Well, the 1 is not going to help us at all. If we look at this relationship here, the only way we're going to get x squared is 5 by the x squared. Okay? If we look at this one, let's say we're going to expand this bracket. Px times px, that gives us an x squared. X squared, x to the 4, x squared px, x cubed. So the only way that we're going to get it is when we do the px times the px. Okay, so then we would have to take in that 10 as well. So if we then look at creating for x squared term, we would be looking at 5 times the x squared plus 10 times this term squared, because it's got a square on the bracket there. So p squared x squared. So if we then factorize out our coefficients, 5 plus 10 p squared x squared. And now we use that other piece of information in the question, that the coefficient of x squared is 95. So, for value of p, we know that 5 plus 10p squared equals 95. So, taking away a 5 gives us 90 divided by 10. P squared equals 9. So, p equals technically plus or minus 3. But remember, given p is greater than 0, because p is a positive constant, they made sure to tell us that. Therefore, p equals 3. So we solved our quadratic correctly, but we have used the information in the question to actually fine-tune our answer to give the specific answer that we need. There is only one answer for p. It is a positive constant. It is 3 alone. So even when the binomials get a little bit more ugly looking, there is nothing really to be scared of because it's still the same conceptual approach. It's just figuring out what have I got that's matching on and how does it match on to what I've been working with before. And how are things linked together to help me understand how to work through this process. So sequences and series, your APs, GPs, and binomials, they can throw some interesting and fun questions at you, but there's nothing to be scared of. You do have the knowledge and the skills behind you to actually start tackling some of these more interesting questions.